Thank you. So, as the title says, I'm going to talk about some tangential Lipschitz gain phenomena. The thing that I missed out in my title is that this is happening in Cn for n greater than 1. So, I want to first start by sort of pointing out certain features in complex analysis of several variables that are patently missing in C1, which is basically makes what several complex variables more interesting to work on. Right? So, I'll first start by talking about these. So, for that we'll need to know what a holomorphic function is. We simply extend the one variable concept to each slot, right. So, a function f defined on an open set in Cn is holomorphic if it's holomorphic or analytic in the one variable complex sense. So, you can expand it as power series about each point, and then you won't have any barred variables, right. The first thing is the Hotdogs extension phenomena, right. So, what this says is that I'll talk about it in an example. So, if you have let us say a ball of radius 2, and then you take out a ball of radius 1, a closed ball of radius 1, and if you have a holomorphic function in this sort of annular hull, then the holomorphic function basically fills in the hole, right. And the only thing you need is that the compacts that you take out, after you take it out, the space is still connected. Now, this is clearly not true in C, right. You take the unit disk, look at the punctured unit disk, 1 over z is holomorphic, which with no extension, right. So, one way to think about this is somehow 0 sets of holomorphic functions in variables more than 1 is a lot more complicated, at least they are not compact. The next thing that I want to talk about involves this notion of pseudo convexity. If you don't want to get too technical about it, and because this is sort of very introductory in nature, you can just think of it as regular convexity, right. But if you want to know a little more about what the pseudo means, basically what we are doing is we are taking convexity and we are taking the part of convexity that is preserved under biholomorphic transformations, right. Another way to think about this is you can think of convexity, real convexity, in terms of the complex tangent space to the boundary. This is basic pseudo convexity is convexity with respect to the complex tangent space to the boundary. Now, there is something interesting happens here as a consequence. Kranz calls this the Tomato-Can principle. We will see in a minute what this means. So, this basically says a holomorphic function extends past pseudo concave boundary points, right. So, somehow pseudo convexity is a natural obstruction for holomorphicity to extend, right. So, we can even see this see a proof fairly quickly too. So, let omega be such a domain, and most of what we are doing is completely local to a boundary point. So, we do not need to think about the whole domain when you are talking about these things. Focus at the point P, the boundary is pseudo concave. Imagine a holomorphic function in omega. Now, if you go slightly above P in the normal direction, the outward normal direction, you can actually fit a complex disk, a one-dimensional complex disk, such that the boundary of the disk is lying inside the domain. Right. Then you can basically write down the Cauchy integral formula that will make sense on the boundary, and then that will let you extend that function holomorphically to the whole disk. Now, move the disk from P all the way on out until the domain is pseudo concave, and then you just extend the holomorphic function. And again, this does not happen in C1, because you draw any domain, you can write down a holomorphic function that does not extend past any of its boundary points. Now, before we move on to the tangential Lipschitz gain, I want to basically agree on some notation and terminology and recall some few facts about Lipschitz functions, and then we will all be set, right. So, omega for us will be a bounded domain with smooth boundary, smooth meaning C infinity, and it will be in Rn or Cn, and the context will usually make it clear what we are talking about. If it is in Cn, then script over omega is the holomorphic functions on omega. Delta of x would be the Euclidean distance of x to the boundary, and nu sub p would be the outward unit normal when p is a boundary point. And we do not want to keep track of constants that are somehow not relevant to the issue at hand. So, whenever we are talking about some sort of universal constants, we will simply drop the constant and we will use the symbol less than with a tilde underneath that, right. And we will say A is approximately B if A is bounded by a constant times B and B is bounded by a constant times A. This just helps us sort of focus on the crucial things, right. Okay. Quick recall of the definition of a Lipschitz function. Let alpha be between 0 and 1, a function f defined on some set in Rn is Lipschitz alpha. It is also called Helder alpha if fx minus fy in absolute value is bounded by x minus y to the alpha. Right. You can also define Lipschitz spaces for alpha equals 1 or higher, but then that's unnecessarily making things complicated. So let's just stick to small range of alpha. Now, the Hardy-Littlewood theorem is a very useful tool when you're studying Lipschitz functions, because the Lipschitz condition is somehow not very easy to check. We have to look at all pairs of points and compute these things. What the Hardy-Littlewood theorem tells you is that you don't have to do so much work. Just look at the rate of blow up of the derivative of the function, right? Now notice that alpha is between 0 and 1. So this is the distance to the boundary of x, and the power there is negative, right? So as x goes to the boundary, this thing here is actually blowing up, right? So what the theorem is saying is, if your derivative does not blow up too fast, you're in some nice Lipschitz class, right? So we'll essentially always use this to show that some function is Lipschitz. And for harmonic functions and as a consequence for holomorphic functions, this is actually also a necessary condition. So it's a complete characterization of Lipschitz functions in those classes. Okay, now let's move on to what we're interested in studying, right? So what's the background of this story of tangential Lipschitz gain? So Stein observed in 73 that if you take a holomorphic function omega, right? Omega is a smoothly bounded domain in Cn, no assumptions about convexity or pseudo convexity. And if it is Lipschitz alpha, then it has to be Lipschitz 2 alpha in the complex tangential directions, right? So you almost get extra Lipschitzness in the tangential directions for free, right? This again has to do with sort of a recurring theme in several complex variables, namely the geometry sort of imposes a lot of conditions on the regularity of holomorphic functions and solutions to other operators, but for now we'll talk about holomorphic functions. Now, what is happening here? So let's look at a trivial case. Let's look at a case when omega is actually pseudo concave, right? We already saw that holomorphic functions actually extend past the boundary. So it's not just Lipschitz 2 alpha in the complex tangential directions, it's actually C infinity, right? So it's Lipschitz all alpha. So this theorem is not saying much in the case of pseudo concave boundary points, right? So then when is it saying something interesting? It's actually saying something interesting only in the strongly pseudo-convex case, right? So to see that, you need to know what is actually driving this theorem. So the key geometric fact behind this is the following. So if you start with a boundary point, drop down delta units into the domain along the normal, then you can fit a complex disk of radius roughly square root of delta in the complex tangential directions, right? Then you sort of write down the Cauchy integral formula for the correct derivatives, and then you can show that that gives you the 2 alpha gain in the complex tangential directions, right? And the other thing is this square root has a close connection to this number 2. So if you're, let's say you had a domain where you drop down delta and you can fit a complex disk of size cube root of delta, then this gain here would be 3 alpha, right? And again, we restrict the index here simply because we don't want to talk about higher order Lipschitz spaces. So once you notice this connection between the square root and the 2, you see that this result is sharp only for strongly pseudo-convex domains, right? So the flatter the domain, the higher order delta you can fit, and then the higher the gain you have. So naturally, people want to understand this better and sort of formulate this result, more sharply, right? So Kranz tried to formulate this. Well, he formulated this in terms of the Kobayashi metric, but unfortunately, we don't know very much about the Kobayashi metric in dimensions 3 or higher, right? Catlin has proved a result that gives you estimates for domains in C2, and using that you can make an effective version of this theorem in terms of this gain. Now McNeil had used a construction of certain non-isotropic polydisks near convex domains of finite type, and McNeil and Stein were able to use that to produce a whole slew of estimates on a lot of different objects in several complex variables. In particular, they were able to capture this phenomena sort of very precisely in this case, right? But that's only for convex domains of finite type, and it's not clear how much you can extend the scaling method, right? I'll come back to this maybe in a few slides later. So we want to understand what happens in other situations, right? So let's look at an example that sort of motivates our work. So consider this domain omega. I'm looking at the boundary point 0. Right? That's the explicit defining function around 0, so you want to think of this locally. The way it's written down, the normal direction is going to be Z3. So if you drop down delta units inside, you will be at 0, 0 minus delta. And if you take a slice of the domain, this is how it's going to look like, right? This is the mod Z1, mod Z2 profile. the graph there is the boundary of the domain. Now what's happening is in the z1 direction you can fit a complex disk of radius delta to the 1/6. Similarly in the z2 direction, but if you went diagonally you can only fit a disk of radius delta to the 1/4, right? Now this is precisely the problem that sort of convexity helps you avoid. If you had two directions in the tangent space, convexity will let you control everything in between, but here we don't have that control. Right? So we want to capture this, so you sort of do the naive thing that you can, namely define a function, pick a unit vector, define a function that measures the largest complex disk that you can fit in the direction, right? So I start with the boundary point, drop down t units into the domain, so this is the boundary of the domain, and then measure the largest complex disk, one-dimensional complex disk that you can fit in the v direction, right? Now if you make some mild assumptions on R, you can actually prove a theorem saying that if R is increasing, then the Lipschitz gain that you get is determined by the inverse of R, right? So if you have t to the 1/6, then the gain is t to the 6 alpha, right? Now I want to note one thing though. So in our assumption, R is compatible with alpha, roughly talks, it's similar to alpha less than 1/2, but here it plays a little more of a role in terms of actually allowing disks of the correct size to be fit in when you do the Cauchy integral formula, right? So it's a little stronger than alpha less than 1/2, but it's roughly of the same flavor. Now let's go back to the example. Now what this says in this example is that if you have a Lipschitz alpha function that's holomorphic, in the z1 and the z2 directions you'll get Lipschitz 6 alpha, but in the diagonal direction you'll get Lipschitz 4 alpha, right? Just like what the intuition from Stein's result tells us. So what do we want to do with this? Of course this is useful only if you can prove sort of robust estimates on S on large classes of domains, right? Which is what I'm going to be working on this year. So I want to relate this gain function S to the defining function of the domain, right? And of course this is not going to be possible probably in all classes, so the question is what large classes can we talk about? A natural candidate is to look at the scaling method used by McNeil and Stein and see if you can extend that, and it looks like you can apply it to decoupled domains and certain domains whose Levy form has comparable eigenvalues and some classes like those. So those we should be able to get this relation fairly easily. The next is this notion of finite type that I sort of touched upon. So finite type basically is an algebraic invariant on the boundary. So it measures the order of contact of complex analytic varieties or even singular varieties. Now the difficulty in SEV has been sort of using this algebraic information to study sort of analytic problems either inside the domain or near the boundary. Now Dwilewicz and Hill have introduced two type functions which relate this boundary information to certain analytic disks that live near the boundary inside the domain. So they've pushed the algebraic information on the boundary to analytic information inside the boundary, and it looks like our gain function is going to be closely related to these functions. So I want to study the connection and see if that provides a route to sort of understanding this better. And ultimately we want to be able to tie all this together in terms of estimates for intrinsic or invariant metrics like the Kobayashi metric, but that's probably a slightly larger project and we probably need a lot of people working on that because right now our understanding is fairly minimal in the direction. I'll stop here.